Today I'm going to be doing a question on momentum, but this question specifically includes sections from other parts of the syllabus. We're going to be doing a little bit of SUVAT, we're going to be looking at a little bit of frictions and inclines, and then we're going to be looking at momentum. So this question comes from the May-June exam, May-June 2020, zone 41, and this is question 7. There's a part A and a part B. Right, so if we look at this, we have a particle of mass 0.3 kgs lying on a smooth inclined plane. Smooth inclined plane at 30 degrees to the horizontal. It is released from rest. Okay, so we know that it started at rest. It slides down the plane for 2.5 meters. Okay, so if we're just going down the plane, from the top to the bottom, that's 2.5 meters until it reaches the horizontal plane. The particle Q of mass 0.2 lies at rest on the horizontal plane 0.5 meters from the end of the incline. Okay, so it's exactly as it looks in the diagram. P collides directly with Q. Okay, it is given that the horizontal plane is smooth. Okay, so we have this horizontal plane here is smooth, and P continues moving in the same direction with a speed of Q. Okay, so once they collide, so P is going to collide with Q. They're going to have a collision, and then once they've collided, P is going to continue with a speed of 2 meters per second. So we'll assume it's going in that way. It's not going, well, let's just see. P continues moving in the same direction. Okay, so it does tell us it's not rebounding. So it continues in the same direction, and so then obviously Q is also going to be going in that same direction. Okay, they want us to find the speed of Q. Right, so if we're looking at our momentum over here, we've got the mass of P times velocity of P plus the mass of Q times velocity of Q, and that needs to be equal to mass P velocity. Okay, so this is all before the collision, and then this is after. This is the conservation of momentum. So when these things collide, the momentum needs to be conserved. So if we take a look at what we've got, we want to find what is the speed of Q afterwards. So we don't know what that is. We know what the mass of Q is. We know what the speed and the mass of P is after the collision. This is at rest before the collision. So if it's got no speed, it's not going to have any momentum. So that becomes 0. We know the mass of P before the collision, but we do not know the speed of P before the collision. So we need to work out what is the speed of P, and we need to work it out in a different way. It's not going to help if we use momentum in this case, because we've got 2 unknown V's in this equation. And our final one that we're wanting is the velocity of Q. So we must be able to find velocity of P in a different way. All right, so if we zoom into P, we can see here we've got a section of constant acceleration. So this thing starts with it starts from rest, so we know its U is 0 meters per second. We know that it's traveling a distance of 2.5 meters. We don't know acceleration, we don't know time, and we don't know the final velocity. Okay, but we can work out the acceleration of this particle if we now just zoom into the forces on the particle. So I'm going to just redraw this over here. Let's just draw a straight line. So that's 30. So what are the forces on this? At the moment, it's only the mass of 0.3 kgs or 3 newtons. Okay, so in mechanics, we just use gravity as 10. All right, so the only thing acting on this particle is that there's no friction and there's no driving force or any other forces acting on it. So we can break this down. I'm going to break it down into its horizontal and vertical components. So if that's 30, we know that's 30 over there. You can use your triangles to work that one out. So if I'm trying to get, let me maybe just make this one in red to make it clearer. I'm trying to get what is this force going down the hill, because that's the direction that this particle is moving in. So if I look at my triangle over here, okay, this is my triangle that I'm going to be working in. If I look at that one, I can see that my two red arrows are the same here. So my sum of my forces in my x direction is equal to my hypotenuse times sine of 30. Hypotenuse times sine 30, and it's the only force pulling this thing down. So I know that it's 3 sine 30. Sine 30 is a half, so it's going to be 3 over 2. This force going down here. We have 2 newtons. So if I need to work out the sum of forces is mass times acceleration, I've got 3 over 2 is equal to 0.3 times A. So my acceleration is going to be 5 meters per second squared. Okay, so now I've got more information from a SUVAT equation. Squared, I'm just going to take all this down. Okay, what do we want to work out? We are going to work out what is the velocity of this particle, because we're trying to get velocity before the collision. And so that's going to be useful for us. So if I want velocity, I'm going to use v squared u squared plus 2as. I know my particle starts from rest, so my u squared is going to fall away. Okay, and so my velocity is equal to 5 meters per second. Just remember to square root it to get velocity. Okay, so what that is telling me, I need to work at a down a section of constant acceleration. So if I go down my blue arrow here, my particle P is going to be at the bottom, and it's going to have a velocity of 5 meters per second. All right. Now, they did tell us in the clue that there's no change in speed when P reaches the horizontal plane. Okay, so it goes down the incline, and then there's no change in speed. So it's also 5 at the very beginning. And what's going to happen now? This particle needs to move across the plane to Q. Okay, so the question is, at what speed is it going to hit Q? Okay, so we need to just look at this particle. I'm going to redraw my forces here. So what are the forces acting on this particle now as it's going towards Q? What are the forces acting on it? We've got its mass acting down, but there's no friction. They said there's no friction acting backwards, and there's no force pulling it forward or anything like that. So actually, this particle is going to continue infinitely going in that direction at 5 meters per second. Now, this is not a realistic situation, but this is the situation in this setup in part A of this question. So although it's not realistic, we need to understand that if there's no friction acting on the particle, it is going to continue infinitely in the same direction. And that's one of Newton's laws, that a particle at rest remains at rest, or a particle in motion remains in motion, unless there is an external force acting on it. All right, so if it does continue, it's going to then collide with Q at 5 meters per second. Okay, and so now we can actually jump into our momentum equation. I'm going to just go directly from what I've already set up here. So as you're writing this, you might need to figure out how to do it a little bit neater, but for the sake of this question, I'm just going to keep going here. So we know it hits it at 5 meters per second. That's going to be 0, and this is equal to 0.3. Then we said it continues at 2, and the mass of P is 0.2, and we don't know what the velocity is. Sorry, the mass of Q is 0.2. Okay, so the only unknown in this equation is what is the velocity of Q. So I'm going to quickly do that. And I get an answer here of 4.5 meters per second. And this is the correct answer. I've just written it. I just made sure that we have the correct answer of 4.5. All right, so can you see we had to first resolve the forces on this particle to understand what the acceleration is. Once we had the acceleration, we could use SUVAT on an inclined plane to get the velocity at the bottom of the plane. Once it's on the horizontal plane, it's no longer accelerating or decelerating, and so we can use that same velocity as it collides with particle Q. Okay, let's go into part B of this question. So it is given that the horizontal plane is rough. Okay, so now everything in this question is changing. Particle comes down. Nothing actually changes from the first part. So it's still going to come down, and it's going to be 5 meters per second that it hits the horizontal. But this plane is now rough. Okay, so as this particle is moving along here, it is now going to have friction, slowing it down. So we just need to bear that in mind. So when it hits particle Q, it's not going to hit it at 5 meters per second. Okay, that's basically how we need to interpret what's going on here. We need to do the calculation to figure out what is the mass going to be, but we need to understand that the particle is now going to be slowed down. Okay, so it is rough. They coalesce. So then they coalesce and they move with a speed of 1.2. Find the coefficient of friction. Okay, so we've got momentum here, and we need to now work out the coefficient of friction. So I'm going to start with what I started with earlier. Mass of Q times velocity of Q is so the mass of P, velocity of P, mass of Q, velocity of Q. Okay, because they coalesce, we're going to end up putting their masses together. We're going to have a velocity. This is actually going to fall away because it's still Q is still at rest. So the mass of P and velocity of P. So let's just see what do we have in our formula already. So we already know what the mass of that is. We don't know the velocity of P. We don't know at which velocity it hits it, but we do have both masses, and they've also given us the velocity of Q afterwards. So we can actually calculate at what speed does this particle hit Q. This is 1.2, and they're going in the same direction. They coalesce and they move. So they're not going, there's nothing that's going to cause them to go backwards. They're still going to go forward, so all of our signs can be positive. We can actually calculate with what speed does it hit this particle. Okay, so you've got to just calculate this. 3. So I'm seeing it hits it at 2 meters per second. Okay, does that make sense? So it started at 5 meters per second at the bottom of the slope, and it hits with 2 meters per second. That makes sense. So it's slowed down. If I got a value that was greater than 5, I would be quite concerned because there's nothing that's going to make this thing speed up. All right, so now you see I'm working backwards here. So at the end of the day, they want me to know the coefficient of friction. So if I take my formula for friction, I'm looking for this at the end of the day. So now what do I need to calculate next? I can work out what is my normal force. Frictional force. How am I going to work out my frictional force? I still need to do something to get to that. Okay. But I have now a portion of constant acceleration. So I'm going to do another SUVAT equation along that arrow, if I can put it that way. So my initial speed is 5 meters per second. My final speed is 2 meters per second. This distance they gave us is 1.5 meters. And I can work out my acceleration. The reason I want to work out my acceleration is because then I can go into my sum of my forces, is mass times acceleration. So all of these questions are like puzzling pieces together. Okay. So if we calculate our acceleration, if you are watching this video, I encourage you just to do each of these calculations, even pause the video and do the whole thing first, and then you can check yourself. Okay, so I get an acceleration of -7. So does the negative make sense? Yes, because this thing is going to be decelerating, and it's decelerating quite, quite a high amount because it's going from 5 to 2 in a very short distance. So that makes sense. All right, if we zoom into Newton's second law, the reason I want to do that is because I'm trying to now find my frictional force. So the only force acting on this particle is actually going to be the frictional force. There's no driving force or any incline or anything like that. So I know I have my frictional force pulling it in the opposite direction. And this thing has a mass of 0.3. And the acceleration is 0.7. So the magnitude of my frictional force is 2.1 Newton. Okay. So my frictional force is pulling us backwards, and you could have, maybe used your signs differently in the way that you did this question, so long as you understand that the friction is acting backwards. So I've sort of taken my direction of motion to be my positive direction. So therefore the force is acting negatively and my acceleration is negative. But you could have done it differently. You should get a magnitude of 2.1 for the friction force. Okay, and then let's just work out our R. So our sum of my forces in the y direction is going to be 0. And the only thing is the weight acting down. So my 0.3 times gravity of 10. So that's going to be newtons acting up. And so then if we jump into our frictional force, we're going to have 2.1 and 3. And that's going to give us an answer of 0.7. And you can see that that is the correct answer over here. All right, so this is what a typical momentum question can look like. So although the momentum formula is still the same, and that's quite a simple thing, it does take a bit of understanding to go from SUVAT into Newton's second law, into momentum, and be able to piece each of these puzzle pieces together as you go. So that's the part that makes it a bit trickier. But as you understand the question and the theory behind the question, you should be able to do that. All right, well done, and that's that for today.